Hi guys, today as part of Intro2Astro, we're going to be talking about exoplanet atmospheres. My name's Barron Nguyen and I'm currently an upper division undergraduate student as well as a dual master's degree at Stanford University. So I primarily look at studying exoplanet atmospheres, oceans, and their planetary evolution throughout time. So with this kind of field, it's really important that we study our own planetary bodies in the solar system in order to extrapolate what we don't know about other exoplanet systems to those that we do know and can study up close in our own backyard. So I'll go into more detail later and also show some cool photos. So let's begin. So this is just a quick little fun slide on the TRAPPIST-1 system. So some of you may have heard of this system. It's quite famous in terms of looking at the habitability of really Earth-like planets. Though these planets do orbit a non-sun-like star, so an M dwarf, roughly 10% smaller in mass compared to our sun. So really small, really t tightly packed system. So what can we kind of learn from this system and what does that inform us about the atmospheres, as well as the habitability and other parameters that we're interested in studying? So just a cool illustration by NASA JPL. So this we're going to go today over atmosphere formation and loss, climate and atmospheric structure, then move on to detection and characterization and what that means for life and habitability. So let's start with the introduction. So I'm going to go into a lot about Earth and planetary sciences. You may think that this geology or earth sciences or atmospheric sciences are not necessarily important for astronomy, but um, going over today's topic, I'm going to try to explain why atmospheric and earth sciences is important for astronomy. So just a quick intro into and something to start you all thinking about the connection between earth science and astronomy. So just like a couple cool photos about some of the things that are connected when we talk about discovering and characterizing exoplanets. Oceans, biology, dune formation, surfaces, and climate. So here's a quick primer on potentially why Earth science is important to astronomy. The first is that planetary surface processes are regulated by atmospheres. This means that cycles that we want to study, like erosion, weathering, volatile cycles, how water or carbon goes through the planetary interior and out, as well as fluvial dynamics on the surface, how do dunes form, for example. The image on the bottom is actually of Namib Dune on Gale Crater on Mars, taken by the Curiosity rover. And you can see that these dune formations are really cool, really strikingly similar to those that we find on Earth, like in Death Valley. So the question is, how do these dune forms? For them to form an atmosphere is really important in order to have some sort of heavy molecular atmosphere in order to carve those dunes through aeolian kind of erosion and flow. The other thing that is really quite important in terms of geophysical connections is the interior and atmosphere connection. So, for example, how we study the evolution of water, carbon, nitrogen, these are actively being cycled in and out of the Earth. This is what we call volatile inventory and outgassing. So, for example, when a volcano erupts, they transport kind of preserved gases in the interior to the surface, as well as looking at tectonics and thermal evolution. How does, for example, the planetary accretion or initial heat from the formation of the world impact the ongoing kind of like heat and surface temperature of our planet? Another really important thing is core dynamo. In other words, how does the rotating core of a certain planet protect its surface and make sure that the atmosphere isn't stripped away by strong solar radiation and solar particles? So that's for the geophysical part. When we look at biology, astrobiology, life and habitability, this is really well reflected in the things that we want to study regarding exoplanets. For example, atmosphere biosignatures. What kind of evidence of biology can we kind of infer from molecular uh, molecules in the atmosphere, whether that may be kind of organic molecules or hints of biology. Oxygen is a big one for Earth, but I'll also talk about later why that is not a great candidate for detecting biology. Another big one, but quite theorized, is technosignatures. You guys may have heard of Dyson spheres. So, how does that tell us about possible civilizations or extraterrestrial life based on what we can detect from our planet and from our observatories, mainly, flux and changes and dips in stellar light. Other things, for example, we might be interested in is water and oxygen predictions. Can we predict oxygen levels, water levels on another planet? Water is really important for life. So maybe having water is a big hint of a planet being habitable. Including other concepts that revolve around habitability in life include having a stable climate, an origin of life, where does prebiotic chemistry come from? This is a big thing with astrobiologists looking at the so-called RNA world. Where does our RNA come from, essentially, and where does origin of life come from non-biotic chemistry. And then another big thing is atmospheric chemistry. The processes that happen in the atmosphere are very important in order to regulate um, possible biology, life, and habitability on the planetary surface. So just a couple quick introductory concepts on the connection between astronomy and earth sciences. So this is a really cool plot from a paper, Tonieta et al., 2023, just looking at the connections between earth science concepts, astronomy, physics, chemistry. You can see that astrobiology is a big one in green. And how does that connect with, for example, atmospheres, oxygen? We see in red ecosystems, bacteria. There are a lot of coupled systems that are really important to study in order to understand the holistic kind of evolution of a planet. And a lot of that time we do that through astronomy, looking at planets through telescope like James Webb, like Spitzer, like Hubble, to kind of inform us about these minute processes. So a mix of observation and modeling is really a big thing in planetary science and astronomy. So that's the introduction. Let's move on to our first concept. So atmosphere formation and loss. So the big question is, where do atmospheres come from? So I'm going to start you off with this question. Just think about that importance. We live every day on the surface of the Earth. We kind of know at the kind of superficial level that plants provide oxygen for us to breathe, and we exhale carbon dioxide and water. But in a more kind of abiotic and kind of primitive Earth sense, where does our original atmosphere come from? So I'm going to talk about a little about the theory behind this. And this is just a cool image I picked up from NASA and JPL on a protoplanetary disk. So these are essentially when the era of the star, quite young, when the star is still accreting. So accretion means getting bigger, swallowing up, dust, gas in order to expand and get bigger. Some of this leftover dust can actually form planets, as you can see on the right hand side. That's like I think a gas giant planet with a little ring system. Where do our atmospheres come from? So they begin really at the birth of a planet at the protoplanetary disk stage. So let's look at first the definitions of a primary versus secondary atmosphere in terms of looking at atmospheres, where they're usually categorized based on their type as well as the stage that they evolve in. So there's two stages, primary and secondary atmospheres. So primary atmosphere is really the original accreted gas from the planet-forming disk. This is the protoplanetary disk, and it's mainly hydrogen and helium. So the same composition as, a star, mostly is hydrogen and helium. So that should be the expected primary atmosphere of a early planet. So something like Jupiter or a Saturn-like planet, a gas giant planet. So the atmosphere is really heavy in hydrogen and helium. The second type of atmosphere that most exoplanet, at least for habitability, are concerned with are secondary atmospheres. So these are all the atmospheres that are not originally accreted during planetary formation. So more heavy molecular atmospheres, these being non-hydrogen and non-helium. Those are really light elements. So we're more interested in the heavier molecules and the heavier elements that form those molecules. So this may be formed through outgassing, volcanic eruption, equilibrium between a magma ocean and its atmosphere, biochemical. This may be studied through biosignatures, what type of molecules are exerted or are evidence or signs of for signs of life. Photochemical, these are interactions between the star's light and the atmosphere. For example, dissociation. How do UV rays, for example, affect the survival of a certain molecular species in the atmosphere. So we're going to talk about this concept more importantly in the next couple slides. So just keep that on the burner. And then atmospheric chemical processes. These are maybe like not only photochemical, but may include, for example, shock waves, meteor impacts, and whatnot. And then geochemical. These are a larger kind of range of chemical and geochemical processes that are really important in understanding, for example, drawdown of oxygen by rusting, for example, can eliminate some oxygen. So a bunch of these like biological, geological, chemical concepts are really intertwined in the formation of a secondary atmosphere. So, for example, you guys may be asking what is considered a secondary atmosphere. So some big examples are water, steam atmospheres, CO2 like on Venus, oxygen and nitrogen like on Earth, methane, can be signs of life, can be also not, like on Titan, where there's some methane, and rocky silicate vapors, which are really evaporated when a planetary surface is so hot that the rocks start evaporating. So these are all considered secondary atmospheres. And this diagram on the bottom by Tian and Heng really shows the planet's forming with a primordial atmosphere, that being hydrogen and helium, eventually loses it and can reform that through outgassing. For example, these two diagrams show on the top maybe like some carbon dioxide water, and the bottom maybe like a mix where that hydrogen is left over, can interact with the outgassing gas, forming kind of gases with some like reactive hydrogen compounds, like methane, for example, or some leftover hydrogen. So that's a quick difference between the primary and secondary atmosphere. And the next thing I want to connect with is this sort of kind of data that we found by observing the radius of planets through telescopes. So a big thing came out in 2017 was this kind of bimodal distribution of planet radii. So you see on the bottom left panel that this 2D view of planet count, so how many planets that we discovered, and the size of the planets, you would expect it to be kind of like a bell curve, a Gaussian curve, one single peak and then it goes down. But instead, we found that interestingly enough, there was a bimodal peak, meaning there are two peaks to the data. And then the red is the rocky terrestrial planets, roughly below 1.8 times the size of Earth's radius. And then the blue kind of area is sub-Neptunes, or planets that are less than the size of Neptune, but bigger than perhaps like a super Earth. So this was a very curious kind of observation made by the early California Kepler survey. And on the right, we have kind of a top-down view of the same data, except with comparing stellar light intensity and occurrence rates. So those kind of dark contours are the two peaks, but in kind of like a bird's eye view. So this is called the radius gap problem. So the big question by atmospheric scientists and exoplanet scientists was what causes the radius gap problem? And a big hint, it was atmospheric loss. So let's talk about that more. With atmospheric loss model theories. So the first big one, which can explain the radius gap, is photoevaporation. So what does that entail? Essentially, intense stellar light can kind of like drive evaporation of hydrogen and helium since it's so light. These kind of atmospheres can absorb the energy, and once absorbing the energy, the hydrogen and helium kind of floats away because it's getting hot. So the big idea is that large planets can hold on to more of their gas because of stronger gravity. We see Jupiter-sized planets, gas giant planets, have that kind of hydrogen helium atmosphere, not just because they're further away from the sun and get less stellar insolation and radiation, but also because they're just bigger. So they have more gravity, they can hold on to that more. And the other thing was high energy radiation, such as extreme UV light, which a lot of times just abbreviated to XUV, can strip away the lighter species. So this is the same thing with, being closer in proximity to your star, you're more likely to lose your initial hydrogen and helium envelope, your primordial atmosphere. There was initially another kind of theory called core-powered mass loss, which instead of that radiation coming from the star could be recreated from the same internal luminosity from a cooling planet being radiated outward. But I think generally that effect is not as large as the stellar radiation. So a lot of the recreated models for atmospheric loss favor stronger photoevaporation, the star being the main culprit of that atmospheric loss process. So that's being shown by that Gupta and Schlichting plot right there, where that radiation is in red and it's kind of coming from the cooling core. There are other loss model theories that are quite important. I won't go into them much, but for example, one is impact erosion, and this is when a big asteroid hits the planet and can kind of carve away and kind of that atmosphere. So, for example, in Sakharova et al., that image shows like a big giant impact can kind of like blow away that atmosphere. So that's another big loss model. But when we're concerned with kind of overall holistic evolution, the bigger role for characterizing whether an atmosphere stays or gets lost or gets stripped is really more of just looking at photo evaporation. So yeah, so another way to kind of view this concept is the idea of a cosmic shoreline. So the big question is, why do some rocky planets like Earth and Venus have large atmospheres? Why don't they get stripped away if photoevaporation is such a big issue? The idea is that there is a big balance between the escape velocity and the amount of extreme UV light that you receive on a planet that can strip away an atmosphere. So escape velocity directly correlates with how big your planet is in terms of mass. Just because a bigger planet has a higher escape velocity, it's harder to leave an orbit when the gravity is much stronger. So a higher escape velocity means that the planet has more mass, essentially. So if we look at this model of a cosmic shoreline, as it's called, which is basically the point where an atmosphere is lost versus an atmosphere is retained, we can really use this as a simple model to gauge whether a certain planet can retain an atmosphere and predict if we could potentially observe an atmosphere. So it's kind of a first degree approximation. Of course, there are a lot of other replenishment mechanisms, atmosphere replenishment, and atmospheric loss mechanisms. So the idea generally is just to view it as a quick, rough first like estimation of an atmosphere on another planet. So this graph by Paz, Charbonneau, and Vandenberg shows that cosmic shoreline graphed by Zonley and Catling in 2017, and we can see that other planets in blue, so Venus and Earth, and some exoplanets too. We can see LHS 11440b have their atmosphere retained because they're below that shoreline where it's has low enough kind of XUV flux from the sun, so not as much stellar irradiation, but also doesn't have as low of escape velocity. So the balance between the two parameters can retain that atmosphere. And everything else we see that like Mercury, for example, is beyond that shoreline. It's in the red. So it probably doesn't have an atmosphere, as we know from observations, that it's a bare rocky planet. So just a little quick primer on the idea of a cosmic shoreline. So I just wanted to show some cool pictures for the secondary atmosphere formation. So compositions and examples that we know of at least. So the formation of higher molecular weight atmospheres that are not hydrogen and helium, not primary atmospheres. So for example, like I said earlier, oxygen, carbon dioxide, methane, water, nitrogen. These are all examples of secondary atmospheres. And just to show a couple more images, both real and illustrations, just to show the idea of what they potentially and do look like in real life. So for Earth, this is a NASA JPL photo. We do know that most of our atmosphere is composed of nitrogen and oxygen, and that blue glow right there is very hints at oxygen. Just a really cool kind of cloud layer. That's also water vapor. Then we have Venus. That is actually the real visible. I think this image was taken by a Japanese mission, actually, not by NASA JPL, by JAXA. So that is actually the layered top cloud layer for Venus, and it's actually really, really white. So these are an atmosphere made out of kind of like sulfur dioxide gases as well as carbon dioxide. So really cool example. And then we have Titan, a really interesting kind of moon, technically not a planet that orbits Saturn. And we can see that there's like an orange haze to the planet. And this is a evidence of methane and dissociated methane species. So organic organic hydrocarbons, though does not come from organic kind of life, but instead abiotic processes then that create methane. So this is really from methane ice, and then it gets dissociated by light into kind of these hazes, these orange hazes. Though Titan is mostly nitrogen as well. It's just that the hydrocarbons and methane are quite strong and appear as really orange that we can see them with some missions. I think this is with Cassini-Huygens, though I might be wrong. Um, and then we have an illustration of exoplanet 55 Cancri E. So potentially new observations and models show that the planet most likely has a carbon dioxide atmosphere, though it orbits really close to its star. So I think the orbital period, or a year essentially, for that planet is less than 1 day. It's like 12, 15, 18 hours. It's like zero point 0.8 of a day. So really quite close to the star. And we can see that it's a lava world, a magma ocean world, but also with a carbon dioxide atmosphere. So just some examples. And then the other big question is, how did these atmospheres form? So mainly, main culprits are accretion and outgassing. So accretion is from the initial planet-forming disk. You get that hydrogen, that helium, and you can kind of sequester that early on into your mantle of your planet. And then you can outgas that again eventually. So this is a big reason potentially why water, where Earth's water comes from, is from the initial hydrogen from the protoplanetary disk. It gets stored as hydrogen in the mantle and gets outgassed and reacts with oxygen in the mantle to be water. And then the big thing is delivery from volatile rich bodies. This is also another formation pathway for Earth's water. Potentially, water-rich ices, asteroids, and comets can deliver water to the planetary surface from beyond the frost line, which is the distance away from the star where it's cold enough for ices to form. And then we have biological pathway. So this is essentially oxygen by plants photosynthesis. We know creates that oxygen in our atmosphere. So this is technically a tertiary atmosphere, but it's not a primary atmosphere, so it can go under the umbrella of a secondary atmosphere per se. And then we have atmospheric chemistry, so dissociation. A big one, for example, is that this association of water vapor in an exoplanet surface can actually produce oxygen and hydrogen. So this is another reason why oxygen is not a telltale sign of life. A big one is that it can be created without the need for life, or another term for it is abiotically. Another big thing is impact shock. When an asteroid kind of hits and comes into contact with the atmosphere, that pressure and temperature at the very tip of the asteroid can create the necessary environments for the synthesis of more kind of rare molecules. So there's a quick few images. So Mauna Loa, we have some outgassing, for example, from a volcano, sulfur dioxide, carbon dioxide, and then an image of Comet 67P. Potentially a water-rich asteroid that, in the past, some similar comet could have delivered some water to Earth via that impact. And then another big thing is biologically, we see, for example, an algae bloom on Lake Erie. Potentially could be signs of oxygen producing in Earth's atmosphere. So that's a quick kind of intro on atmosphere formation and loss. Then we want to go more into the details of climate and atmospheric structure. So a big concept in exoplanets is the idea of a planetary equilibrium temperature. So this is essentially, you can think of it as the expected surface temperature of a planet based on the incoming stellar radiation it gets from its star, and also the inherent radiation that a planet radiates away. So for context, everything in the universe basically, unless you're at absolute zero, emits some sort of radiation outwards. So you may have heard of like a heat map, like we give off heat, infrared radiation, and that's the same idea essentially. Just because we have some like inherent level of energy, we can emit light, though we don't see each other as glowing, so it's not an optical light. Usually it's an infrared light for us, for mammals. So this is the equation. We have for equilibrium temperature, it basically is derived from and kind of like rearranging the variables for by balancing the incoming starlight and then outgoing long wave radiation. So sigma is just the Stefan-Boltzmann constant. L is the star's luminosity. In watts, A is unitless, that's the Bond albedo, or the fraction of reflected light. So, for example, something with very high albedo reflects most of its light. Something with low albedo absorbs a lot of the light. And then A is the distance from the star to the planet. Usually, it's because a lot of planets don't have perfect or not perfectly circular. Usually, the semi-major axis is used. Earth's calculated equilibrium temperature, you plug all these units in, it's roughly 255 Kelvin. So that's a little below what's expected, and I'll leave it up to you, and also talk about later why that is the case. But we're going to go over it in the next couple slides. So a big thing I want to go over too as well is the idea of atmosphere emission and absorption profile. So this goes back to the that everything kind of has that outgoing long wave radiation from planets. For people, it's the same. The sun and Earth emit at different wavelengths to the black body radiation. So if it's more hot, it has more energy. So it emits at a higher wavelength, more energy wavelength. So for example, the sun, a lot of it is, if you see this graph right here, that orange curve, it peaks around a lot at the really high UV, and that's why we wear sunscreens, because the sun has so much energy that it's kind of emitting light at a lot of it in the UV range. And then we look at the spectra for Earth, actually. It's emitting some light, not as hot as the sun in the UV range, but it is emitting some light at a lower kind of wavelength, and that's in the infrared. And that's what the Earth is losing in terms of energy. When it absorbs that light, it's emitting it away to space via infrared. What you also see in this is that the idea of a perfect black body where it should emit in kind of like, it's not exactly a bell curve, but a sort of kind of curve, is that there are gaps and holes. And this comes from the idea that gases in the atmosphere absorb emitted light from the sun. So a big one is the ozone layer. We talk about the Montreal Protocol. Why preserving the ozone layer is so important is because it absorbs a lot of that light, a lot of that UV light emitted from the sun. And if you can see on the bottom panel, the components of absorption, and we look at oxygen and ozone, all that pink is really in the UV range. So that's really important for making sure that that UV light doesn't reach the surface of the Earth. And then the big thing when we talk about kind of like global kind of climate change is that CO2 and water absorbs a lot of infrared radiation. So if we look at water vapor and carbon dioxide, we see that those absorption kind of like strength areas is located really in the infrared area. So that's the idea why if you stack up all these um, kind of preferred absorption of the gases at specific wavelengths, and you stack them and you merge them all together, you get this total absorption scattering for Earth. And you can see that the emitted uh, outgoing long wave radiation is in the negative space um, of the absorbed, just because it emits everything that isn't absorbed by these gases. So that's just another really quick, important kind of primer on atmospheric absorption. And we'll go into and talk a lot more about how this concept is really important for detecting atmospheres in the later section, because this is the basis of using, for example, spectroscopy to figure out what gases are in exoplanet's atmosphere based on what light we're not receiving from the star. So the other thing, kind of big thing I want to go into is about the greenhouse effect and the runaway greenhouse effect. So these are concepts important for understanding both why CO2 and water vapor and other gas species can affect habitability of an exoplanet, but also kind of explained by their absorption bands at specific wavelengths that we just went over. So, for those who don't know, gases at certain parts of the atmosphere absorb Earth's emitted radiation and reflect it back to the surface, kind of like a greenhouse. That's essentially where the name comes from. But some clouds do reflect incoming solar radiation due to reflectivity or albedo. We talked about Bond albedo. That's exactly the same. It's not the same as geometric albedo, so I won't go into that, but just know that when I use albedo in this kind of lecture, I'm talking about Bond albedo. So again, it goes from the scale of 0 to 1, it's unitless, and 1 being absorbing zero being absorbing awe, and one to being reflecting awe. So one would be, for example, the albedo of a mirror. Zero would, for example, be the idea of like a really black object that absorbs everything, every light. Um, Another big thing I want to mention before I forget is the idea of black body radiation. If you guys have ever seen a hot piece of metal glowing red, that's exactly the same reason why it glows red, is just because that it's so hot that there is some light emitted from it. So that's the same concept. I just wanted to have that quick example before I forget. But going back to the greenhouse, um, the runaway greenhouse concept is based on the effect, but essentially it's a positive feedback loop where if we have a planet where there's increased temperature, there's more evaporation of water. And because warmer air holds more water vapor, as you know, if you go to the equator, that increases the temperature because water vapor, again, is a greenhouse gas. And once that happens, it eventually gets warmer and it's a cycle. Increased temperature leads to more evaporation and then more uh, increased temperatures. And then once that happens, oceans can evaporate. And when the oceans evaporate, it exposes the bare rock. And this can lead to carbonates decomposing and weathering. So carbonates are found in rocks. They're a group of minerals, and this releases CO2 essentially. So you have this positive feedback loop that when we have more water and more carbon dioxide, it actually leads to more kind of water, more CO2 being released, leading to a runaway greenhouse. This isn't the case for Earth, just because we don't have um, a sudden rise in global temperatures over a long period of time, millions and millions of years. But that happens, for example, on a planet like Venus, where we've seen that the atmosphere is all made out of carbon dioxide. So just a concept that we need to understand in order to kind of look at the limits of planetary habitability, which I will go over later. So another big thing is we need to understand the vertical structure of an atmosphere itself. So you guys may have learned this in your science class, essentially the layers of the Earth's atmosphere and other planets as well, not limited to rocky planets, but for example, gas giants as well, like Jupiter. So these are called kind of atmospheric temperature pressure structures. So these TP structures depend on radiative heating and cooling properties of the atmosphere. So molecules can kind of release heat and absorb heat. So for example, the troposphere, radiation heats the planetary surface. So we see that temperature decreases with altitude. For example, Mount Everest is much more colder than the when elevation is zero. Um, for example, we have a decrease then, as you see this, both these at the troposphere, which is basically that decreasing temperature line. And then we have, interestingly enough, an increase in the temperature once it hits the stratosphere, and that's the transition between the stratosphere to the from the troposphere to the stratosphere. That inflection point is called the tropopause. So stratosphere, it doesn't decrease its temperature all the way to space just because in the stratosphere we have UV absorption by certain molecules, aerosols, cloud particles, whatnot, that increases the temperature with altitude. So we see this inflection point, for example, in this kind of plot by Catling, 2014, where they show the comparison between the troposphere, which is below the dotted line, and the stratosphere, which is above the dotted line. The dotted line is a tropopause of the vertical structures of each planet in our solar system. We can see that all of them reflect nicely except for Venus. And so I'll leave it up to you guys why this is not the case, but a hint, it is because of the kind of absorption and reflectivity of the carbon dioxide in and the properties that they hold for cloud formation as well in the upper atmosphere. And then we have like a little vertical structure for Jupiter showing the troposphere and stratosphere. So it's the same as this, but instead showing the clouds. Just as you can see that we don't just have water ice clouds. We have ammonia clouds. We have haze clouds made by kind of carbon dissociated hydrocarbons. So just a cool diagram on different clouds at different parts of the vertical structure of the atmosphere. So this leads us to our next idea I want to talk about quickly is cloud formation and the idea of exotic clouds. So clouds form essentially when the partial pressure of a condensable vapor at a specific altitude exceeds the saturation vapor in that local region. So this sounds like a lot of mumbo jumbo, but essentially the idea is that a saturation vapor pressure is the pressure, a specific number, a pressure of a liquid vapor system where the rate of evaporation is equal to the rate of condensation. So if you put a jar, like a glass jar of water and cover it, that the water in your jar will evaporate right into the air inside the jar. But since it's a closed system, essentially when you're evaporating, that it's going to reach a point where there's so much water in the air, so much water vapor in the jar that it kind of rains back down and condenses. So this loop, once it reaches equilibrium, where there's an equal amount of water evaporating and also water condensing because it's humid in the jar, that is our exact saturation vapor pressure, that pressure of the water vapor in the jar. And then the partial pressure is just the pressure of a gas in a certain space. So a mixture of gases, for example, if there's equal parts hydrogen, water and carbon dioxide, then the partial pressure would be like half of the total pressure for water and for carbon dioxide, for example. So it's when the partial pressure of a certain kind of area exceeds that kind of saturation vapor pressure point, and then it condenses. That's all it's saying for cloud formation to happen. And clouds are important because we can observe clouds through photometry, which is basically the amount of light we receive from a star, and spectroscopy, splitting those light into wavelengths. And that they can give us insights into atmospheric composition and cloud movement. So, for example, this is actually really cool, is that um, some kind of people study brown dwarfs, which are kind of failed stars or giant, well, not giant planets, but kind of substellar. They're called substellar planets that are much larger than, for example, a Jupiter-sized planet, but not enough to become a star. By studying the amount of light that they kind of emit, we can kind of make a map of the cloud. So this is actually a really cool kind of model of the observed clouds on Lumen 16b by Crossfield et al. In 2014, where they kind of map the clouds on the brown dwarf. And then on the right, we have the idea for cloud formation, where at a certain temperature and a certain kind of partial pressure, we have starting from A. If it gets cold enough, things condense. But at the same time, if it's humid enough, we can increase and also hit that zone where clouds form. So that's a cloudy and foggy region for the space here. So yeah, that big idea is that clouds are not limited to water. So on Earth, all the clouds that we see are water vapor. They're white and fluffy. But interestingly enough, on exoplanets, that's not necessarily the case. We have on Jupiter, for example, though not an exoplanet, ammonia, sulfur clouds. Also water ice clouds, but also a lot of ammonia sulfur, and that's the orange stuff. And then on a really hot planet, we have corundum clouds. So these are ruby clouds. On other planets, we have steam, we have really dark clouds, we have sulfur clouds. So we also have like evaporated rock clouds. So the big idea I wanted to show you with clouds is that we have to think outside of the box and look at the formation of clouds that are not just water. So this is a really cool photo taken by the Juno probe by NASA JPL, and this is a real colored image of Jupiter's clouds when that probe flew by, and you can see all these swirls in different colors are different clouds and made of different compositions. And since certain clouds form at certain layers, we can actually see that for example, the blue clouds are more deep the atmosphere than like for example white clouds. So just a lot of movement and very pretty photos I just wanted to show. But yeah, the next idea is detection and characterization. So how do we actually study something so far away that we can never ever reach? A big thing I already said earlier is that we can study our own solar system planets in order to learn more about the compositions and evolutions of exoplanets. But there are methods to kind of observe them with telescopes. So I think someone already went over this, but essentially, generally, planets are detected by the transit method. So this is like a pure chance thing where the planet kind of eclipses the star from our view, at least, that we can see a dip in the starlight when we observe it over time. That dip hints at a planet. So we do require transits in order to study the atmosphere because the starlight needs to kind of interact with the atmosphere in a certain way in order for us to see kind of a change. So the big thing is what we can do with a primary eclipse when when a planet passes in front of the star, we have transmission spectroscopy. So this is, I'll talk more about it, but essentially kind of look at the absorption of certain gases in the atmosphere. And then with a secondary eclipse, when the planet passes behind the star, we can use emission spectroscopy if the planet is hot enough, where the added reflection of starlight from the planet, just because it's at an angle, that it kind of like adds up to both the star and the planet's light together. And then we have a full phase curve where you can see that kind of transition between the total light between the star and the planet evolve over time as an orbit. And we have to kind of decompose those kind of added elements because we see it as a curve, an increase and a decrease and a dip into kind of their discrete components. What fraction of the light comes from the star, what fraction of the light comes from the planet. So this is with a full phase curve. You can use both emission spectroscopy or study potentially the albedo of a planet. So this could be just the surface of the planet. This could be due to clouds. So just a quick primer. The big thing I'm going to go back again, and this is central to observing atmospheres and understanding them, is the molecular and light interaction. So this is absorption and emission. So absorption is the idea that I went over again, is that certain gases absorb light in different wavelengths. So ozone again absorbs more UV, CO2 absorbs, and water absorbs more infrared. This is why a lot of the new telescopes sometimes prefer instruments prefer studying planets in the infrared range is because different kind of missions are more favored in different wavelengths. So if you want to study atmospheres, infrared is probably your best bet. Um, so this is the big idea of absorption is the basis for transmission, where the starlight passes through the planet's atmosphere when the planet eclipses over the star, and we can see that absorbed effect when we view the star. Um, and then emission spectroscopy. Gases can re-emit radiation based on vibrational energy received by absorption radiation. And when I mean vibrational energy, I mean that, like, for example, in water, we have those kind of two hydrogen bonds, hydrogen molecules bonded, hydrogen kind of atoms bonded to the oxygen, and they kind of like vibrate a little and twist and turn. And these can reflect and re-emit at certain wavelengths as well. And this is most obviously used on hot planets just because, again, hotter planets can have more of an emitted radiation because they're at a higher temperature. So this is the basis for emission spectroscopy. So on the left we have an Earth-like exoplanet transmission spectrum. So this is basically the same plot I showed before, looking at which gases absorb where. We can see that over here, this big increase is the ozone, and we have the dips that we saw below, mainly attributed to water, to water vapor, to CO2, some to methane. And then we have an emission spectrum. What light does a planet give off that hints of an atmosphere? And this is a example emission spectrum from a big hot Jupiter planet, and we can see that looking at the spectrum, there are dips and also increases in light, and that can be attributed to certain molecules in the atmosphere. So blue is water, yellow is like silicates, so these are like evaporated rocks, and we have carbon monoxide and other species like methane as well. So let's go over more about transmission spectroscopy in detail. So this requires a primary eclipse transit, so the planet eclipsing the star from our view to observe the light passing through an atmosphere. So there are some pros and cons of this. It's sensitive to upper atmospheric absorption, but it's not really good for probing the low atmosphere. And then there's a degeneracy, essentially, or there are two meaning that there are two kind of interpretations of a flat structure. One can be attributed to like you just don't see an atmosphere at all. That's called a bare rocky planet, or it's being reflected away or and blocked by clouds and hazes. So this diagram on the right really shows the idea that the starlight the stars are over here, we're over here, our detector is over here. The light passes through the atmosphere, and the atmosphere absorbs some of that light away. And then the gaps in the spectra we see are hints of the molecules in the atmosphere. Then again, this is the second kind of middle image shows that the that if it's really close, the planet is really thin and close and hugs the planet tightly, we might not be able to observe it, just because it requires a lot of light passing through an atmosphere in order to see a hint and trace of it. And then we have the appearance of clouds and hazes can actually block the light. So this is shown by the bottom panel, but it can also be shown here, where we, from what we see, we just see a dip in the light, right? And if there's a big atmosphere, high atmospheric absorption, meaning that the molecules absorb a lot of the light, versus low, it just looks like the planet may be bigger. So it can either mean that the planet is just there's just no atmosphere, but the planet has a larger radius, or it means that that kind of difference is the evidence of atmosphere. So how we figure out whether it is a bare rocky or there is an atmosphere, we kind of have to kind of compare the density of the planet, and compare it to if it didn't have an atmosphere versus if it did. So lower density means that like the radius is slightly bigger than what we expect it to be if it was only a rocky planet. So that difference in density can hint that there is something going on with an atmosphere. Then the second big one is emission spectroscopy. So it requires a secondary eclipse, or when the planet passes behind the star, or a full phase curve, looking at both the primary and secondary eclipse and recording a full year for the planet around the star and measuring it continuously. So mostly this method is used to observe the emitted light from the planet itself from the day side of the planet. For example, this photo shows a diagram of the star in the middle, and this is a planet. It's tidally locked, like the moon, always faces the Earth. It's in a certain position, so a rotation of the Earth is the same as, sorry, a rotation of the moon is basically is synchronously kind of coupled to its rotation around the Earth. So one side always faces the star, so it's always hotter. So we can see that just because that one side is hotter, it emits more light, versus when it passes right before it eclipses the star, we're seeing the night side, so it does not emit as much light. So we can see that difference in the amount of light it receives right before the secondary eclipse and right before it does a primary eclipse, and do some simple math just to see that light difference. So this can most importantly used to establish a thermal profile of a planet and characterize or possibly characterize heat redistribution. So if we see that what parts of the planet should be hotter or should be cooler, we can kind of think about that. There should be redistribution, just like for example on Earth, where 2 o'clock is actually the hottest time of day, not noon, just because of that atmosphere kind of like trapping and making the heat linger. And we can also establish kind of like a 2D view of the planet and see where that heat is deposited, like a heat map, but for the planet. So I just wanted to show some examples of secondary atmosphere observations by transmission spectroscopy. So this is again the light of the star passing through the exoplanet's atmosphere. This is an example from 2014, GJ1214, observed by the Hubble Space Telescope. So the planet's equilibrium temperature is around 580 Kelvin. So like an oven, essentially, as hot as an oven. And the results of the study were quite unremarkable, at least in the first glance. There was a flatline spectra caused by clouds, flatline spectra again, right here. So they were like, oh, what is going on? But the results were showing that it was being blocked by clouds and hazes. And that's why we see all the observed lines. So these are the dots right here. These observations taken by Hubble are more or less in a flat line, rather than if we viewed like it through a steam atmosphere without clouds, it would rise, it would go down, peak at 1.4 microns, and then go back down again. But we didn't see that happen. So it must have either been a bare rocky planet or been blocked by clouds and hazes. But it can't be possible to be just a bare rocky planet, because there were some previous studies and also some observations that ruled that out. So it had to be clouds and hazes. And a newer study showed that the phase curve measurements and also climate modeling suggest that there is some steam component in the atmosphere. So the hazes, even though they were not able to quite kind of figure out the composition of the atmosphere, just that the clouds and hazes exist, this new study we're showing that potentially these clouds are like the clouds we have on Earth, kind of the white, fluffy water vapor clouds. And this is just a quick simulation of that thermal map generated by a climate model, showing where that the bright is much hotter and then the black and then the dark red is much cooler um, of the planet. Yeah, quite cool. We can use climate modeling. So the other thing is emission spectroscopy. So this is a observation, quite new, of a secondary atmosphere observed on 55 Cancri E, which is a sub-Neptune rocky planet. Um, I think like 40 light years away, or was it 12? Yeah, I think it was 40 light years away, roughly, of a carbon dioxide and carbon monoxide atmosphere. So this was taken by James Webb Telescope, and we can see that this is the result of that observed measurements. We have the black dots are the measurements that JWST took, and then the colored lines are basically the expected kind of emission profiles, depending on the fake models that these researchers looked at. So if it was carbon and dioxide and carbon monoxide it would look like we would expect it to be the red line. So it really fitted with that line with either carbon dioxide or carbon monoxide. So really interesting that we see this sort of like Venus-like atmosphere in another planet. And just to note that this planet again orbits very closely to its star. It's an ultra short period planet, so a year is basically one in less than 1 day, and it orbits a sun-like star, so very, very, very hot. And then we have TRAPPIST-1c on the right. So the group of kind of like big planets that people love to study about planetary habitability. B and C are quite close to the star. I think the habitable zone for TRAPPIST-1 is around TRAPPIST-E and F. So again, the preliminary observations by, I think this is, oh yes, this is a quick dot by using JWST, using a secondary eclipse. That kind of one data point shows that potentially it's just a bare rocky planet, which we expect just because it's orbiting closer to its star, so it should be stripped relatively quickly. Something maybe like a Mercury-looking planet, perhaps. So that's it for the detection and characterization. And then I want to talk about the implications regarding life and habitability, because that is a big kind of like question and area of interest for a lot of people. So again, the habitable zone. What is it? I know some of you probably already know about this concept, but I'll go over it more in detail and kind of specify more about its definition. So it's the distance and region around the star where water exists as a liquid. So at first, this can be quite potentially like easy to figure out. You can just measure the equilibrium temperature, but that is just an approximation. Really, you need to figure out and then the true definition really is that the outermost or coldest part of the habitable zone is defined as the maximum greenhouse warming potential caused by gases such as CO2 or water vapor. So how much can you have of an atmosphere that raises the kind of planetary surface temperature that you would expect, not from just like a bare rock planet? And then the innermost region is set by the runaway gas limit, where, like we talked earlier, the amount of greenhouse gases that contribute to kind of a really hot and oven-like planet. So as you can see, this green area is really defined as the habitable zone. We have Venus right here, and that's in the red zone, definitely not habitable. Earth is smack dab in the middle. Right here, and the maximum greenhouse is just a bit over Mars. So that's why Mars is also really big interest for people to study, just because potentially in the past it may have been habitable, but spoiler alert, at the peak of habitability or the wet era for Mars, I think it was called the Amazonian, was essentially as plentiful of water as Death Valley today. So not a lot of water, but potentially at the outer limits of habitability. So this is a cool image, kind of plot gathered by the Habitable Worlds catalog from the University of Puerto Rico. So they really have plotted the sizes of the planets. So we have Earth-like planets, Terran planets, Jovian planets like Jupiter, the Neptune-like planets, Neptunian, and also planets that are slightly bigger than Earth, super Terran or super Earths, and then slightly smaller than Earth, sub-Terran or mini Earths. So these are just all the planets or the exoplanets we discovered that may be in the habitable zone. Doesn't mean they're habitable, but it just means that they're in the zone. Um, so the habitable zone. is not too cold and not too hot. I actually wanted to show this kind of like GIF because it shows the application of a global climate model. So when we talk about climate science and why that's also really important into studying astronomy is that we can use the exact same models that are developed for Earth to study consequences of kind of like climate change and apply that to exoplanets to study, if we had this atmosphere composition made of CO2, this fraction of water, this fraction of this gas, and then orbits away from the star at this distance, what would the planet's surface temperature look like? So interestingly enough, these climate models, or known as global climate models, GCMs, can give theoretical insights into the complex climate behavior and habitability beyond simple equilibrium temperature calculations. So for example, this kind of plot by the University of Bern shows that if Earth was only 15% further away from the sun, the Earth would be frozen in 20 years. So this is actually a really cool kind of climate evolution. A plot right here where the right is the surface temperature, red is hot, kind of light blue is really cold, showing that the temperature over 20 years. And then on the left, we have the world starts out as the global ocean, but the white is the ice cover. And basically, the last places to freeze are the equators, which makes sense. The hottest part of the planet just because they receive more sunlight than, for example, at the poles. So just a really cool concept that the habitability is very sensitive to zone and very sensitive to atmospheric properties. So just because, again, the planet is in a habitable zone does not mean it is habitable. Um, we need to look at the full picture. So just again, comparison of the TRAPPIST-1 system with the inner solar system, our habitable zone is way, way, way further away from the TRAPPIST-1 habitable zone. As you can see that it orbits in the inner much closer than Mercury is to our sun. We know Mercury to be like a very hot planet. It doesn't have atmosphere. It's a very extreme planet. But for them, the habitable zone is actually way closer. And this is because our star, the sun, is a G-type star. So it's way more hot than, for example, M dwarf star, which is much more cool and much more smaller. So M dwarf is 10% the mass, roughly, of the sun. So the habitable zone for TRAPPIST-1, the star, is much closer than the habitable zone for like a sun-like star for us, for on Earth. So this is the big system that a lot of people like to study in order to see the possible habitability, not only for exoplanets in general, but for stars way more different than ours. So yeah, the conclusion slide essentially is connecting it back to life and biological activity and the idea that atmospheres are really important for that process to happen. For example, they protect from harmful solar radiation, from cosmic rays, from thermal variability. If you have a day on your planet jumping from a couple hundred degrees from the night side to the day side, that's going to fry everything on the night side and freeze everything on the cold side. So that's not very helpful for having long-term evolution of life, just because you want something stable for growth to occur. And then atmospheric detection methods can possibly explore biosignatures in exoplanetary candidates. So this is the big thing right now. A lot of astrobiologists are really interested in is what can we learn about the atmospheres of other planets and connect that back to possible hints or molecules or gases in the atmosphere that hint at extraterrestrial life. So for example, maybe some of you have heard of this on the news the past few months, but a team discovered a dimethyl sulfide and dimethyl disulfide on K2-18b, which is like a super Earth sub-Neptune size. So I think it's roughly the 8 times or 7 times the mass of the Earth, around 2 times as large in terms of radius, to be signs of biological life. The reason was the thinking behind this is that on Earth we only know disulfide and dimethyl sulfide to be produced by stressed phytoplankton and bacteria on Earth, in oceans on Earth. That connection, that explanation was that if we see that on another planet, there must be life, but not so fast. More recent research has shows that there are abiotic ways to create dimethyl sulfide and dimethyl disulfide via atmospheric chemistry, for example, and it evaluates the original detections of DMS and DMDS in the original transmission spectroscopy. Doesn't mean it's completely ruled out, but it does reduce the chance and likelihood of seeing that gas in the atmosphere, just because a lot of the time we're trying to um, kind of see the dips in the atmosphere that we receive when the starlight passes through the atmosphere to kind of like infer a certain gas, but all of the time it's also statistics. When does that dip? When is that dip in signal to noise ratio strong enough that we can declare a certain certainty that there is this amount of gas in the atmosphere versus if the dip is perhaps not as strong, then we have a less statistically likelihood of declaring that a certain gas in the atmosphere. So statistics is also really important in evaluating the substance of or strength of an atmosphere detection in a planetary atmosphere. So I think this was just a quick fun slide to round things off. Again, if you go back to our question, why is atmospheres on Earth science important to astronomy? Maybe you guys now have a much better sense of the connections between biology, chemistry, geophysics, geology, and studying the holistic evolution information of extrasolar planets. So yeah, thank you so much.